All right, we are recording. We are live. Audio and video is up and running. Hope everybody had a wonderful weekend. We are in lecture 24. We are rocking and rolling in here. A couple quick announcements. So I'm going to start grading homework 5.3 today. Again, we assigned 5.3, but then on Friday we discussed some means by which you could make 5.3 a little easier by using different coordinate systems and defining your origin in certain places, and maybe using two coordinate systems again to integrate from either side. Again, a number of tips and tricks that we can use to make that problem easier. So I'm going to start grading that today, maybe sometime tomorrow. So again, giving you a little bit more time on that. I see that in the chat. One of the things that can help if you ever have audio issues or video issues is if you turn the cameras or the mics off, it can reduce the amount of data that you're transmitting. It can help with connection issues. And if you all have any issues with me, let me know. I don't know if you're talking about your end or my end. If anything drops out, let me know. I'm going to assign homework 5.4 today, and then this is actually going to be our last day on deflections, because we could talk about deflections till we're blue faced, but there's not really a lot to cover conceptually beyond what we've covered for virtual work. I'm going to do a virtual work example for beams, and then I kind of want to talk about something I've actually never talked about in structural analysis before. I want to talk about shear deformations, just to kind of give you a little bit of a larger picture as to what's going on in the world of structural analysis and deflections. Let's recap a bit. So up until now we've been looking at virtual work for beam deflections, and I also want to recap what we did for trusses, right? So but first off, let's handle it one step at a time. So to compute the deflection of beam, we need essentially two sets of functions. We need the set of real moment functions, which we use a capital M, and then we have the set of virtual functions, which we use a little m. And beyond that, we need the flexural stiffness properties, and by that we mean the modulus of elasticity, and we need the moment of inertia I. Once we have all that, we just sum up all of our integrals, and then there you go. There's our deflection. Beyond that, the only thing we have to consider is some unit conversions. Now, to sort of round out a bit what we've talked about in the past little bit and what we're talking about today, I want to just maybe generalize the principle of virtual work a little bit. So what we've been doing is we've been integrating these terms little m, big M over EI dx. And so we've been summing up all of these integrals and saying that if you sum up all these integrals, that's the deflection. And remember, what we're doing is we're summing up the energy, okay? And so maybe a term for this, if you want to rewrite this, is you could say that this is the flexural energy. Now for beams, because beams primarily experience bending, right? I have a beam here. I take the beam and I put load on it. It bends, right? So really that's all you need for capturing the deflection. But this expression really wouldn't work if I was looking at, say, a truss. So for a truss, maybe what I would do is, instead of integrating little m's and big m's, I'd integrate, I don't know, little f's and big f's. And do that, okay? And so this would be a new term for energy, and we would call this the axial energy. Now, what we do when we look at trusses is we say, we have an integral here, but the forces in a truss member are all constant. So all these terms are constant, so I can factor these out and just sort of rewrite it like this, which is what we did when we did truss deflection. But the idea is that I can define an energy that represents the axial deformations and an energy that represents the flexural deformations. Well, is that it? Is that the only energy that you can see in a structure? No, there's a lot more. So for instance, what if I had a member that was being twisted? So I might have a little t, a big T over GJ, and then integrate those, and that might be my torsional energy. What about the shear? What about thermal effects, and so on and so forth? And so I can define energy expressions for the different types of effects that a given structure is seeing. The point I'm making is that if I wanted to generalize the principle of virtual work, what I've got right here, this is how you compute the deflection for beams, but in order to do that, I'm only considering the flexural effects. What if I wanted to consider other effects like axial effects or shear effects? Well, in order to do that, I'd need more terms. So I propose that if you want to generalize the method of virtual work, you can add up a series of effects. So, what we've been doing for beams is only considering, the flexural deformations. Well, what about the torsional deformations? What about the axial deformations? What about the thermal effects, and so on and so forth? When we compute deflections, really what we've been doing is we've only been considering the terms that are relevant. So, like, for example, when we did trusses, when we analyze a truss, we make a certain set of assumptions. And one of the assumptions that we make is that trusses only experience axial behavior. So when we did truss deflection, we really only used this term. And in fact, we made it even simpler than that because all the terms in that integral were constant. So we just summed up little f, big F, L's over EA's. So it was just a sum. It wasn't a sum of some integrals. Now, the point I'm making is, well, what about if we have something like a frame, okay? Well, if you're looking at a frame at a minimum would experience not only flexural effects, but it would also experience axial effects. So maybe a simplistic way of looking at it is, beams experience bending, trusses experience axial load, and maybe frames experience both. Frames experience both axial effects and flexural effects. So what we would do in order to compute frame deflections, if we were being a bit general, is we would do two separate analyses. We would do, again, we would have a structure with the real loads present, and then we'd have a structure with all the loads removed and only a single force or moment present at the point of interest with a magnitude of 1 in the assumed direction of deflection. And so we would have not just a series of moment terms that we would have to sum up, but we have axial terms as well. Now, if I was being general, if I was, trying to be as non-specific to frame behavior as possible, then this would be an expression that we could use. However, what you'll find is that, when you actually look at the numbers and you look at the proportion of answers that you get for frame analyses, you can usually just neglect the axial deformation term and just not worry about it. In fact, on your homework assignment, I'm going to have you compute a frame deflection, and I'm going to tell you just do the flexural, don't worry about the axial. But in order to convince you of that, I have a problem here I want to work through. So we have a frame here, and I want to determine the vertical deflection at point A using the method of virtual work. Now, for all of the members in this frame, we're going to keep everything constant. We have an E value of 30,000 KSI. We have an A value of 4 square inches and a moment of inertia of 800 inches to the fourth. Now, without getting too in depth on this problem, one of the things I'll tell you is that this problem, those section properties are actually designed to make the member a bit flimsy axially. To give you some perspective on that, I'm opening up my steel manual, and I'm looking at, let's say, a W18 by 50, which has a moment of inertia of 800 inches to the fourth. Its cross-sectional area is like 14.7, and I'm here made the cross-sectional area 4. So I actually purposefully made this member flimsy axially. But again, you'll see that the axial deformation doesn't really matter at all. And I'm going to demonstrate that by just going through both and showing you how that works. So let me break out the notebook here, and let's take a look at this problem. Okay, so here's the problem, and first thing you'll see is I have the structure drawn twice, and the reason why we have it drawn twice is because this is a deflection problem. We have to perform 2 sets of structural analyses, and so we're going to have to look at the real the real structure, and we're going to have to look at the virtual structure. Somebody raised their hand. Hold on. Yes. Mr. Enoch.
Just before I try to like problem with you as you do it, I just have a question about the sign convention for bending moment and the shear forces when you flip axes. On the homework problem, we went over how it's convenient to look at the structure from a different perspective. You know, put the axes at the end of the beam, or in this case, like with a frame. You know, I'm assuming we'll be moving the coordinate axes, but you also went over the sign convention for the positive shear forces and the positive bending moments, and that was when you're making a cut and looking to the left, positive shear is down, and when you're making a cut and looking to the right, positive shear is up, and same for positive bending moments. So is that the same? Flip those?
That's an excellent question. That's an excellent question, and you're gonna be surprised at my answer. It doesn't matter as long as you're consistent. I'll explain why. When you go back to truss deflection, okay, let's look at truss deflection. When we do a truss deflection problem, we have a table and we list all our little f values and we list all of our big F values, right? And if you remember, one of the things that we said at the beginning is we're just going to assume tension is positive. Remember that? Well, what would have happened to our final answer if we assumed compression is positive? And the answer to that is nothing, because if you're looking at your real structure and you're looking at your virtual structure, if you change your assumption that, okay, compression's positive, as long as you do the same thing on the virtual structure, then the sign convention washes out. So to give you an example, let's take a look at this this structure here, the problem that we're looking at, okay? And I'll go ahead and tell you that what we're going to do is we're going to look at two coordinate systems. We're going to put an x1 from A going like that, and we're going to have an x2 from C going like this, okay? So let's just think this through, okay? So let's cut a section for the beam, okay? So you're talking about reverse coordinate systems, okay? So let's cut a section, and so we're going to have an x2 right here as well, okay? And let's cut a section and look towards x. So over here on the real structure, I'm going to have a fixed support, and I'm going to have this distributed load. And then over here, I'm going to have a fixed support, and like I'll end up having nothing other than the reactions, but you'll see what I'm talking about. Okay, so this is my coordinate system on either end. Okay, I propose that if you're defining your moments, if you define your big moment like this, as long as you define your little moment the same way, the sign convention washes out. Because ultimately, the only convention that you care about at the very, very end of the problem is the assumed direction of deflection. So let's go back to this problem, okay? The focus of this problem is to try and determine the vertical deflection at A. So I'm going to put a single, unit load right here at A, okay? If I get a positive answer, that means that this value here indicated the deflection's going downward, and that assumption was correct. If I get a negative answer, it means it's actually deflecting upwards. The point I'm making is I could very easily flip this and put that down. And there'd actually be nothing wrong with that as long as I'm consistent and that one goes down as well. And the same thing works for shear. Although we don't need shear functions for virtual work right now because we're just integrating, little m and big M. So as long as you're consistent, you can actually do it whichever way you want. Because that's the only thing that matters, is that what direction you assume. Did that answer your question?
Yes. I think I need to wait and see the homework solution for the homework that we just turned in, and then just because that's
no worries. And I'll admit, like, all of the homework assignments I've given this semester, I'm fully aware that one was probably the most challenging. Like I know there's a lot of calculus, a lot of integrals, and like I mean, part of that's kind of by design, But the idea is if you can understand that assignment, and even if you had some trip ups when you did it, if you understand that assignment, you can understand literally anything I could throw at you. Well, let's chug through this a bit. Okay, so let me get back to square one here. So I've got here a real structure and a virtual structure. Now I'm going to assume that the deflection at A goes downward. So I'm going to put a downward vertical load here. Okay. So I've got a real structure and a virtual structure. The first thing that I probably ought to do, and maybe I'll move this over so I got a little bit more room here because I don't want to crunch this. Put that right there. Okay. First thing I probably ought to do is let's compute our support reactions. Now, hopefully by now you all can compute support reactions. In other words, if I just told you that over here on the left, this vertical reaction here is 70 kips. The horizontal reaction is 20 kips, and then the bending moment reaction is 600. Is that okay that I just tell you that, or do we need to walk through that? I'm happy to walk through it if we need, but hopefully by now that you all are good with computing support reactions. Likewise over here on the right, if I compute the support reactions, I got one down, I'm going to have one up, and then my moment reaction is going to be a couple here that's 20. And you know, if you remember from statics, the two 1 kip loads generate a force couple. That's 20 going, you know, was that counterclockwise? So the 20 needs to go clockwise. That should be pretty easy. Okay, so that's the first thing I need to do. Second thing I need to do is define some coordinate systems. Like I said, I'm going to have an origin right here with the x-axis facing that way, and an origin right here with the x-axis facing this way. And so I need to do the same thing on both sides. Okay. So before I move on, is everybody okay with this? Okay, this is the real structure and the virtual structure side by side. I've got the reactions solved for both ends, and I've got the coordinate systems defined for both ends. One big thing is you got to be consistent. You have to use the same coordinate systems on the real structure that you do on the virtual structure. Because if you use the same coordinate systems as well as the same assumptions for positive internal moments, positive internal forces, etc., then the only sign convention that really matters at the end is that right there. Everybody good?
So you're saying that the sign convention has to be the same, the relevant cut in the virtual structure, but not necessarily like if we needed to make 2 cuts on that beam with the distributed load on it, then the axes and the conventions would not need to be the same as long as I'm still maintaining uniformity through each cut, virtual and real.
As long as your sign convention is consistent with both the real structure and the virtual structure, that's all that matters. So, for example, if you say tension is positive, then tension needs to be positive for both the real structure and the virtual structure. If you assume counterclockwise moments are positive, well, then you need to assume the same thing for the real structure and the virtual structure. As long as you maintain that consistency, you're not going to have a problem. Did that answer the question? I don't want to gloss over it.
Yeah.
All right. Now I'm going to do something a little different on this problem because, look, here's the thing. In the end, I need a series of virtual moment functions, real moment functions, and I'm ultimately going to get virtual axial loads and real axial loads. Normally, up until now, we've done the real structure first and then done the virtual structure first. It honestly doesn't matter which one you do first because you have to do both of them. I'm going to do the virtual structure first because I have something I want to look at. Okay, so I'm going to cut a section. First off, okay, let's look at this from sections perspective. Let's take a look at the column, the vertical member, AB. How many moment functions am I going to need to define the real and virtual moments for member AB? Like, how many sections am I going to have to cut through member AB to fully define those responses? One, exactly right. There's no intermediate loads between member AB, so I just need to cut a section. Whether so I'll cut a section here. We'll call this section 1-1, and we'll cut a similar section here. All right. Now, what about the horizontal member, the BC, the beam, if you will? So if I use the term column and beam is the horizontal, column's the vertical. How many sections am I going to have to cut through the horizontal member to fully define that response? One, exactly right. So we'll cut, something like this and like this. All right. Let's look at the virtual structure first. Okay. So let's just follow along. So section 1-1, and we're going to say looking downward. All right. Now, so here's the section. This is 1.0. All right. Now, I propose that we're going to have an unknown axial force. So let's draw that in tension. It doesn't matter. I could draw it in compression, but let's just, let's just pick something and go with it. And then I'm going to have an unknown moment. Now, in terms of sign conventions, especially because we're talking about frames, I could draw this thing whichever way I want. It doesn't matter. As you can see, I've drawn it counterclockwise. As long as I do the same thing over on AB, as long as I draw it counterclockwise over there, I'm good to go. Now, let's do that. Now, help me out. Can anybody just look at this member? So keep in mind, hold on, this dimension here is x1. What is little f going to be, and what is little m going to be? Should be pretty easy by just looking at the free body diagram. Let's start with little f. If I got one going down, got to have one going up. And the little m, if I have nothing acting transversely, then little m is 0. So let's call FAB +1 and MAB 0. And these are valid. These are both, now keep in mind, these are both functions, right? These are valid from x1 equals 0 to x1 is 10. Why 10? Because the column AB is 10 units or 10 feet tall. Okay. Now, I'm going to do a similar analysis over here. So now let's look at section 1-1, looking downward. And I'm going to make a point about this. And some of you probably kind of already could probably guess the point I'm going to make. All right. Again, be consistent in your sign conventions. So I drew F up. F needs to go up. I drew M as counterclockwise. M needs to be counterclockwise. Now, let's do this one at a time. Now, you stole my thunder, Mr. Blizzard. You're exactly right, though. You're exactly right. Let's deal with F. If I have 10 going down, FAB is positive 10 going up. And then to respond to what Mr. Blizzard said, he's absolutely correct. The answer for moment AB is who cares? Because when I'm doing the deflection, keep in mind, what am I going to do? I'm going to say the integral of little m AB, I need to make that a subscript, AB times big M AB over EI dx1, but that's going to be the integral of 0. And so that's going to be 0. And so the point I'm making, and this is what I said at the beginning of the problem, I said we're going to do the virtual function first, because by doing the virtual structure, you can see that MAB is 0. So who cares about what the real MAB is? Because when you integrate them together, it's all going to be 0. And that's it. I mean, he's exactly right. So maybe what I'll do is I'll say x1 equals 0 to x1 equals 10. Box that up. And then maybe I'll erase this. And do that. Okay. Before I move on, I really want this to be clear, and I want everybody to understand what we're doing. Is everybody good? Any questions? This is important stuff. All right. Let's look at section 2.2. And I'm always going to look towards the origin, okay? So when I cut a section, I look to the right. I know there's a fixed support there, but I could either cut a section and look towards that fixed support, or I could cut a section and look towards all that mess on the other side of the section. Keeping in mind, my distances aren't x's, they're going to be 20 minus x's, so there's going to be a lot of oiling if I look to the left, so I'm going to look to the right. All right, so when I cut a section and look to the right, you're exactly right. That's 100% right. You said it probably better than I could, but seriously, you're 100% correct. All right, so when I cut a section and look to the right on the virtual structure, all I see is I've got the unit vertical reaction, and I have the 20 concentrated moment. And then what I'm after here, I'm after the little f and little m. Okay. So first off, we know that little f is going to be 0 just by looking at it. This dimension here is x2. So now I probably ought to sum moments at, so that I do this, right. So when I sum moments at the cut, I don't have to consider the f. I do need to consider the little m. I've got 1 times x2, and I've got 20 going this way. So m plus 20 is x2. M is x2 minus 20. So I get a little f BC is 0, and MBC is x2 minus 20. And then again, that's from x2 is 0 to x2 is 20. Okay. Is everybody okay with that? All right, so now let's do section 2.2 over here. Again, look to the right. And again, the key issue here is to just be consistent. So we cut a section, look to the right. So maybe I'll scroll up a bit here and make sure that we remember what we're going to see. So if I cut a section and look to the right, I'm looking right here. So if I cut a section and look to the right, I'm going to see the distributed load. I'm going to see all the reactions over on the support at C, the 70 kips, the 600, so on and so forth. So So first off, before I start labeling any of the forces, remember, I have little f drawn to the left. I need to have big F drawn to the left right here. I have little m drawn, what is that, clockwise. Big M needs to be drawn clockwise. Now we're going to have a similar conclusion with the that we did on section 1, but just bear with me and we'll see what we get here. So we've got our reactions, which our reactions are 20 kips. This is 70 kips. And then that bending moment reaction of 600 foot kips. This dimension here is x2. Maybe I'll hold on. Move that a bit so I got a little bit of room. Okay, so this distributed load was 3 kips per foot. So I'm going to collapse that into a single distributed load. We'll call that 3x2. And that moment arm is x2 over 2. All right. Did I do that too fast, or is everybody okay with that? Now, if I sum moments at the cut, start the left, work your way over. Okay, so I don't need to consider the F. I've got the M I need to consider. I've got 3x times x over 2, which is going to go this way. So 3x x over 2. I've got, let's see, over here, I don't need to consider the 20 kips. I've got the 70 times x2, and then the 600 goes here. And there we go. So m plus 600 plus, and then 3x times x over 2 is 1.5x squared equals 70x. So what do we get? We get an m, and maybe I'll call this MBC is, we got 70 minus 1.5 x2 squared minus 600. And then as for F, what does F equal? I mean, if we're really being honest, what does F equal? I mean, I can look at it. It equals 20. You're exactly right. But it's also, who cares? Why is it who cares? Because the little FBC, the associated FBC, is also 0. So there's no, it doesn't really matter. Oh, I forgot something. This is x2 is 10, or sorry, of 0. Sorry, what else? Oh, equals 0 to x2 is 20. All right. So if I'm looking at the method of virtual work, let's start off with the flexural part. So the flexural deflection is going to be the sum of all the integrals of little m over EI. Okay? To write that out, what I'm going to do is this, is I'm going to say, okay, we have 1728 over EI times the integral from 0 to 10 of little MAB dx1 plus the integral from 0 to 20 little MBC dx2, right? But if you remember, if I go back to the little MAB was 0, and I didn't even bother deriving big MAB because this whole integral is going to go to 0. I don't even have to worry about it. All I have to do is 1728 over EI, and remember E was 30,000, A is 4, I is 800. Okay, and so I integrate from 0 to 20. This was x minus 20. That's the little MBC. The big MBC I just derived, 70 x2 minus 1.5 x2 squared minus 600 dx2. And so I got to believe you all can do that problem. I'm out. When it's all said and done, this is just integration. So just do that integral, multiply it by 1728, divide it by E, divide it by I. When it's all said and done, you get a flexural deflection of, let me find it, 3.36 inches. And it comes out positive, so our answer was correct here. Now, here's the point I'm making. What happens on the axial side? When you do the axial deflection, so you're summing up the, these integrals, but remember, all the terms are constants. So if you factor out the constant, you're integrating dx from 0 to L, so it's just the sum of little f, big F, L over EA. And remember, that's the exact same thing we did for trusses. It's not like it's any different. And so I'm going to have, therefore, a little f AB, a big F AB times the length of AB plus little f BC, big F BC, LBC over EA, since the EA terms are the same. But it, again, just like with the other one, there was a term we could cancel. And if you go back up here, the BC terms, we had a little f BC of 0, so we didn't even bother with the big F because this whole term goes to 0. And so all you do is you say, okay, little f was 1 for AB. Big F AB is 10, I think it was kip. Yeah, that's kips. And then E is 30,000 KSI. A is 4 square inches. And then the length of that member was 10 feet. And what you got to do is you got to take that member length and convert it to inches. With flexural, the deflection factors, or the conversion factor, 1728. With axial, it's just 12 because you're just doing one conversion. And when you chug this out, you get an axial deflection of 0.01 inches. So before, do you remember I was saying that you could sort of just neglect the axial deformation That's why. I mean, when you do the math on frames, you find that the axial deformation is so negligible. It's so tiny. And I'll bring back the notebook up here in a second in case anybody needs to copy some of this down, but I kind of want to just show you physically why that's the case. Here's my little rubber beam mock-up. And the reason why that term was so tiny was just because of physics, okay? Here's this beam, and I could take this beam and I can bend it all day long. And I could easily take this beam and bend it to, 3.3 inches deflection. That's pretty easy, okay? Now imagine trying to take this member and stretching it, 3.36 inches. I mean, I'm sitting here yanking on it. I just can't do it. I know I'm not very physically intimidating, but the point I'm making is that elements, and this is just kind of physics, are usually much more stiffer axially than they are flexurally. Like they're a lot flimsier flexurally than they are axially. Like I couldn't take this thing and stretch it, 3 inches to save my life. I can bend it 3 inches, no problem, just because it has a very weak flexural stiffness, but a very strong axial stiffness. When you go back to the math bore that out. See, I mean, look at what we got. We got that if you consider the flexural deflection only, you're going to get a deflection of 3.36 inches. So maybe if I wanted to summarize the answer, I might say, considering flexural, the deflection is 3.36 inches. But considering flexure and axial, the deflection is 3.37 inches because there's that, the frame does stretch a little bit axially, and it stretches enough to generate an extra 100th of an inch in deflections. So let me ask you a question. If you were trying to tell somebody how much this frame deflected, do you really need to consider that extra 100th of an inch in the grand scheme of things? No. So a lot of times when we're doing frame deflections, we just don't even bother with the axial effects because it just doesn't matter. And again, I designed this problem so that the member was flimsy axially. In real life, that effect would be even less. So again, frame deflections, don't even worry about the axial effects most times. It doesn't matter. Now, when you use RISA, which is what we're going to talk about on Wednesday and Friday, RISA will automatically assume axial effects. So if you're doing a homework problem and you compare it against RISA and there's a slight difference, this is one of the reasons why, is because it considers axial effects. There's another reason why, and I'll talk about that here in a bit. But before I move on and sort of discuss my last deflection topic, are there any questions? I really want to make sure this is clear. This is good stuff. All right. Now this is, to me, this next topic, look, I'm going to be honest, I'm not put this on a homework or an exam or anything, but I think this is really important for your development as an engineer. So if you go back to what we've talked about before, you can generalize the method of virtual work, and you can consider axial deformations, you can consider flexural deformations, so on and so forth. Let's talk about this. Okay, so let's take thermal effects, okay? Unless you're taking a structure and heating it up or cooling it down, which that does happen in real life. I mean, if you have a bridge out in the environment, take a bridge in West Virginia. We've had days in the summer that hit the upper 90s, and then we have days in the winter that get below zero. That's a heck of a change in temperature, and so that's going to result in a lot of thermal expansion and contraction. That's doable. Now, what about torsion? Okay, well, torsion, if you're not twisting a member, you don't need to consider that, but if you are, you can plug and chug. Normally in civil engineering, we try and avoid torsion as much as possible. Sometimes it's there, but we try and avoid it whenever possible. But one thing we haven't talked about is this term right here, the shear deformations. This term right there. we've never incorporated it in any of our problems. And so why is that? And how would you incorporate it? Well, first off, let's talk about the method. So let's talk about shear deformation. So what I mean by a shear deformation is instead of an element bending, I'm talking about it deforming in shear. I'm talking about it doing what you see here on the top right of the screen. So it actually just sort of doing an angle change. Now, in order to apply virtual work for shear deformations, you would do it as you do anything else. Instead of a little m, big M, it's a little v and a big V. So you would have a virtual shear function and a real shear function. Now, in terms of the other properties that go into the expression, I'm not going to derive the shear deformation equation for you, but rest assured, what ends up getting plugged into the mix is you have a G term, which is your shear modulus. I have modulus of elasticity. That's actually an error. That should say shear modulus right here. I'll fix that on Blackboard. Let's say shear modulus. You have the cross-sectional area of the member, and then you have this term K. K it's just a numerical quantity. It's called a shear shape factor. What ends up happening is when you do all of the math and you derive the expression, there's a bunch of terms left over in your integral. And if you evaluate those terms for whether or not your beam is a rectangle or whether or not it's a circle or whether or not it's an I-beam, like I have here in my hand, you get different values for K. And so I'm going to show you an example here in a second, assuming a W shape. I'm curious, you all, or some of you all probably in civil engineering materials, you might have looked at steel rolled shapes and W shapes before. For those of you who haven't or who are planning on taking me for steel design, we actually don't really use the term I-beam anymore because of the way that we manufacture rolled steel products, using modern methods. We use the term W shape. W stands for wide flange section. So the flanges being the top and bottom portion of the section. And that constant is going to be 1 for shear for W shapes when you use the area of the web. Now let me get to the meat and potatoes of it. We haven't considered shear deformations because maybe we ought to have a discussion as for when shear deformations matter. Like when do they actually have an impact? And the short answer to that is shear deformations really start to matter when beams get deep. Okay, so usually in structural engineering, most beams are fairly slender. So if you look at this little beam mock-up I have right here, a elementary way of describing a beam's slenderness is the ratio of its length to its depth. So if I took the length to depth ratio of like this beam, maybe it's like, I don't know, like 20 or 30 or something like that. I'd have to measure it. But this is pretty typical, and most beams are fairly slender. But there are some instances where that's not the case. And whenever you have a beam that's fairly deep, you start to get into a scenario where shear deformations really matter. And what do I mean by deep? This is a rule of thumb. Don't take this to the bank. But if your L/D ratio is roughly 10 or less, then you should really start to consider the effects of shear deformations. And so some common examples where that might matter is if you're looking at a building and you have a shear wall in a building, that's really just a really super deep beam with the like a cantilever beam sticking out of the ground. But another one is more near and dear to my heart in Bridgeland is a pier. Is that if you look at this component here of a pier and you idealize that as a cantilever beam, that is a really deep cantilever beam. And so normal just little m big M over EI would not be enough to compute the deflection of that beam. Now granted, this is also a tapered beam, so it makes the integrals a bit more difficult, but even if this was just a solid depth, it would be deep compared to its length. And so I want to show you some numbers. So check this out. I have a really simple problem. So this is a simply supported beam with a uniformly distributed load. And I used some numbers that were real. So I put 3 kips per foot on a 25-foot long beam. And as for the different sections, I actually pulled out my steel manual and I said, okay, what are some real life section properties here? Now, just to make sure everybody's clear on how you would do this problem, right? This is 3 kips per foot. This is a 25-foot long beam, right? And so this is a 25-foot long beam. We can have some reaction here, some reaction there. And so if I have, reaction here, cut a section, look that way, you're going to get like a moment function that's something like r times x minus 1.5 x squared, because 3x times x over 2. And so if that's your moment function, for your shear function, you could just take the derivative of that and get that. And so you do the same thing for your virtual function. And so I've got to believe that you all can determine the deflection of a beam, pretty easily at this point. But I want to show you what happens when you start using different shapes. Okay, so Steel Design 101, let's say a W14 by 26. The 14 tells you about how deep it is, and the 26 is how many pounds per foot the section is, how heavy it is. And notice the 3 rows in the table. Each row uses a section that gets deeper, right? The bottom row is a W36 by 135. So its L over D ratio is well below the 10 mark. Well, what I did is I said, let's take these sections and let's compute the deflection. This deflection here in this column here is just what we would do in class. This is what I would expect of you to be able to do. But what if you also computed the shear deformation using a similar process? And in this process, K is 1 because it's an I-beam. Well, what happens is the shear deformations start to have an impact. Now to be clear, as you go down the rows, the deflections themselves just get smaller. And I mean, I didn't change the load, and all I'm doing is making the beam bigger. So if I make the beam bigger, yeah, of course the deflections are going to get smaller. But look at the comparison between shear and flexure. Like when you start to get, you could think of those comparisons as sort of like a percent error. Like if you ignore the shear deformations, you're going to have like a 1.9% error for 14 by 26, which is not that big of a deal in the real world. But on a W36 by 35 or by 135, that's a 10% error. That's a big deal. So I'm not making you do that, but this is just a view into the real world. If you ever have a beam that you're designing or analyzing and it's really deep in comparison to its span length, you need to consider shear deformations. RISA does this automatically, and we'll get into that on Wednesday. Which, by the way, all of the notes for RISA, I've actually uploaded them all in advance. I really think you ought to take a look at them, just peruse them, give them the once over, because I'm going to go through a lot of details really quick on Wednesday before we get into our examples, and given them a once over would really help. That's all I have. Again, everybody install RISA because we're going to start using it Wednesday and Friday, and that's all I have. You got a homework due Wednesday, and with that, I will see you all on Wednesday. Hope the rest of your week goes very well.
By the way, did you get my email earlier?
I did, and the short answer here. Hold on, let me stop the recording. Short answer is don't worry about it.